Good morning, everyone. I decided to break Chapter 13 up into two videos. The first video will focus on the double integrals, and then the next video will focus on the triple integrals. So on the first page here, I have all the formulas that you need to know for our double integrals. The one that is most commonly misdone is the surface area. So since it is area, you want to think that we're integrating a double integral as well. We're going to go ahead and dive straight into double integrals. My focus for the majority of this is going to be setting them up, especially with the change of order of the integration and also into polar as well. So starting with this first one, integral from 0 to 8, integral from cube root of y to 2, e to the x fourth dx dy. The very first thing you want to do is actually figure out what the region is that you're integrating over and graph it, because then it's easier to set up the bounds for your change of order of integration. So here, our x variable is on the inside, so x is between the cube root of y and 2. So if I want to graph this, you want to think for the left side here, y equals x cubed. So y equals x cubed will look something like this. And x equals 2 is over here, let's say. And then y is going from a value to a value. So my region of integration, the values of y are between 0 and 8. So y equals 0 is down here. And nicely enough, this point is at 2, 8. So this is my region of integration. Now, as it stands, it's pretty hard to integrate, so we're going to do a change of variables here. So instead of dx dy, we're going to rewrite this as a dy dx. So ex to the fourth dy dx. So doing that, now I have to think of what values of y is falling between. And the innermost function you want to think from curve to curve. So you want to think what function is defining the lower bound of y, which is y equals 0, and what function is defining the upper bound of my region, which is y equals x cubed. So now my bounds for dy are 0 to x cubed. Dx being on the outside is still the values that x is spanning over this interval. So looking at my graph, x is between 0 and 2. Now you can see this is easy to integrate because if I integrate with respect to y, holding x fixed, I get y e to the x to the fourth, evaluated from 0 to x cubed, dx. Substituting in my bounds, I get the integral from 0 to 2, x cubed, e x to the fourth, minus 0. And now we can integrate this very easily with u substitution. So 1/4 e x raised to the fourth from 0 to 2, 1/4 e to the 16 minus 1. Now I want to focus on just setting things up. So average value, we're going to take the volume of the solid over this particular region and divide it by the area and get the average height for this. So first thing I have to do is actually figure out where these two intersect. So if I set these two equations equal to each other, I get 2x equals 5 minus 2x minus x squared. Solving this out, I get x squared plus 4x minus 5 equals 0. Factoring x plus 5, x minus 1. So it looks like they intersect at 1 and negative 5. So down here, this is the point negative 5, negative 10. And up here, we have the point 1, 2. Alright, I'm going to set this up two ways just so that you see the difference. So I'm going to start by figuring out which one would be the easiest. Well, this region here, you can see there's a clear top and a clear bottom. So if I were to draw that rectangle, and no matter where that rectangle is drawn, the parabola is always the upper bound of that rectangle, and the line is always the lower bound of that rectangle. So this is what's called a vertically simple graph, which means dy dx should be pretty easy to set up. So our average value formula is the integral of the region, so xy dy dx, or the area of the same region. So for the area, we're going to put in a 1 for the integrand, dy and dx. Now technically that finds volume of height 1 for the solid, but numerically it's going to give us the same value as if we were to do area. Now we need our bounds. So dy dx. dy is a lower bound to upper bound. So the lower bound is the function 2x, and the upper bound is 5 minus 2x minus x squared. So same thing down here, 2x, 5 minus 2x minus x squared. And then the upper bound are my x values, so x goes from negative 5 to 1. Now, I do want this to set up, at least for the top half, dx dy, so you notice the difference between this. Dx dy, let's just focus on the top. So if you look at dx, what that means is I need to figure out my functions that define the left side for the value of x, and the right side which defines the value of x. But if you draw this horizontal line in, notice up here, only the parabola is being used to define my left and right side for x, as opposed to down here, where the line and the parabola are being used. So if I do want to set this up dx dy, I'm going to have to do it in two pieces. And to do that, I also need the equation for x. So going up here, first thing I need to do is figure out what x equals for both of these. So y equals 2x. That's pretty easy. That's going to be x equals y over 2. And then for y equals 5 minus 2x minus x squared, I'm going to have to complete the square for this. So let's see, that would be x squared plus 2x equals 5 minus y. Completing the square, x plus 1 squared equals 6 minus y. And solving for x, we're going to get x equals negative 1 plus or minus the square root of 6 minus y. So that makes sense because I should have two equations, one for the left side of the parabola and one for the right side of the parabola. So I'm going to start with the region here in red. The region in red, if I write this average formula, it would be the integral of xy dx dy. Dx bounded from left to right, so on the left side is my parabola defined for the left equation. And the parabola defined for the left side of the equation would be negative negative 1 minus the square root of 6 minus y. The right side of the equation would be negative 1 plus the square root. And then if I define it for the other, the y values, so look at my parabola. The y values for this start at y equals 2 and go all the way up to the vertex, which is at 6. So my bounds for y would be from 2 to 6. Now I can add to this the integral for my other piece. So my other piece, my double integral, would be xy dx dy. X on the left side is bounded by the left side of the parabola, so that's negative 1 minus square root of 6 minus y. And on the right side is bounded by the line, y over 2. And the y values for the blue region are from negative 10 to 2. So that would be the top of my average value. And since I'm too lazy, I'm going to go ahead and use my original one for the bottom. Negative 5 to 1, 2x to 5 minus 2x minus x squared dy dx. Alright, so again, the bottom line of double integrals is we're trying to find the volume underneath the surface over a particular region. And I want to do this one 3 different ways. So the volume that I'm trying to find for the surface, x plus 3y squared, that's what's going to go into my integrand. Over a particular region, that's what's going to go into my double bound. So this here goes into the integrand. That's what I'm going to put into the integrand. And this part here defines my r. And you typically don't put them together into the same integral, or you don't combine them into the integrand or the bounds. So they do stay separate ideas. So first let's graph this. X squared plus y minus 4 squared equals 16. That's going to be a circle centered at y equals 4 with radius 4. So it looks something like that. I'm going to start with dy dx for my first one. Okay, so dy dx means I need to solve for y in my particular equation here. So x squared plus y minus 4 squared equals 16. Solving for y, I'm going to have, let's see, y minus 4 squared equals 16 minus x squared. which means y is going to equal 4 plus or minus the square root of 16 minus x squared. And that's to represent the top and bottom for the curve. And then I need my x values, but I do know that it's a circle of radius 4, so that means x goes from negative 4 to 4. So my dy dx integral is going to be my double integral of x plus 3y squared dy dx. Y is going to go from bottom to top, so my bottom function is going to be 4 minus the square root of 16 minus x squared. My top is 4 plus the square root of 16 minus x squared. And then dx are my numbers from left to right. So my left number is negative 4, and my right value is positive 4. So that would be dy dx. Now let's do this dx dy. So dx dy, now I need an equation for x from the circle. So x would equal plus or minus the square root of 16 minus the quantity y minus 4 squared. So setting this up dx dy, double integral, same integrand, dx dy. The left side of my region would be the left equation for x, so that would be negative square root of 16 minus y minus 4 squared. And the right side would be the positive 16 minus square root, or minus y minus 4 squared. And then my y values for this, now again, it's a circle of radius 4, so it's starting at 0 and it's ending up at 8. So y would go from 0 to 8. That's the dx dy. Now, the last one I want to do is polar. So remember the conversion to polar, dx dy equals dy dx, but that all equals r times dr d theta. This is it, so 3 colon. So same thing, I'm going to set this up. Now, my integrand, I have to convert to polar, so x equals r cosine theta. And y is r sine theta, so 3r squared times 4 theta. R times dr and d theta. And the first I need to figure out are my r bounds. So r starts from the origin, and then if you want to imagine extending radially out, the outer radius is being defined by the polar equation defined by the circle. So I now need to figure out what the equation for the circle is in polar. The original circle was x squared plus y minus 4 squared equals 16. So if I multiply this out, I get x squared plus y squared equals 8y. Now converting to polar, that would be r squared equals 8r sine theta, or r equals 8 sine theta. So the upper bound for my r is 8 sine theta, and my lower bound is 0. Now I need the values of theta that integrate out or trace out the entire circle, which would be 0 to pi. So that is my polar version of the same problem. Let's do a quick review of center of mass. Center of mass, there were basically a ton of formulas, so I want to just review each one. I'm actually going to make the density here a little bit easier, so I want to make the density equal to k of xy. So we'll start with mass and just take it from there. Mass, if you think of this in terms of science, our density, because it is a lambda, is like mass over area. So basically what I need to do is multiply my density times area, and that will give me the mass of my lambda. So my area is where the double integral comes in. So this one, all the way back to example 1, would have been the integral from negative 5 to 1, the integral from 2x to 5 minus 2x minus x squared. And that's going to generate my area, so all I need inside is the density, which is k, dy dx. And I went ahead and typed this on my calculator, so we have some numbers to work with. So this comes out to be 36k. The moment with respect to the x-axis is represented by the mass times the distance to the x-axis. So my mass is the double integral part, negative 5 to 1, 2x, 5 minus 2x minus x squared, k dy dx. But I want to multiply this by the distance away from the x-axis, and that's a y value. So y times k times dy dx. And putting that into the calculator, I got negative 72 over 5k. So similarly, the moment about the y-axis is going to be the integral from negative 5 to 1, from 2x to 5 minus 2x minus x squared. The distance to the y-axis is going to be x this time, k dy dx, and that equals negative 72k. And now my center of mass, x bar, y bar, is the moment with respect to the y-axis over the mass, and the moment with respect to the x-axis over the mass. And that comes out to be negative 2 and negative 2/5. Similarly with this type of problem, we talked about inertia. So inertia is mass times distance squared. So we have our inertia with respect to the x-axis, which is going to be negative 5 to 1, 2x, 5 minus 2x minus x squared. So this will be y squared this time, k dy dx. And that value was 16272 over 35k. The moment of inertia with respect to the y-axis is going to be negative 5 to 1, 2x to 5 minus 2x minus x squared this time, k dy dx. That equals 1044.5 over k. And then we talked about the polar moment of inertia, which is I sub 0, and that equals I sub x plus I sub y. So adding these two up, I get 4716 over 7k. And then last but not least, we talked about what's called the radius of gyration, which was labeled x double bar and y double bar. So x double bar, y double bar is equal to the square root of iy over m and the square root of ix over m. So substituting our values above, I got square root of 145 over 5 and 2 square root of 3955 all over 35. Basically, a lot of formulas, either you'll be asked to put it in your calculator or you're just going to be asked to set up all the integrals and then show me which integrals you would use for center of mass, radius of gyration, that kind of thing. Now, last thing I want to do is the surface area. So, the function again that I'm trying to find the surface area of is f of xy. So that goes into the integrand, and then what's left over, this piece and this piece, is being used to define r. So again, two separate ideas, and so one key thing you always want to figure out is what am I actually trying to evaluate, and then what region am I trying to evaluate that function under. This one I will do two different ways. So first let's graph it. X squared plus y squared equals 1 is my unit circle. I'm going to make this a little bit easier again, sorry. And I'm going to actually change this to an x, so we have a little bit of variety. And I'm going to make this inside x squared plus y squared and inside x squared plus y squared equals 2x. Okay, so inside the unit circle that I just drew, and then over here, if I rewrite this, this would be x squared minus 2x plus y squared equals 0, completing the square, x minus 1 squared plus y squared equals 1. So I purposely did that because I wanted one circle on the x-axis and compare it to a circle on the y-axis. The last example, we had one on the y-axis. So if I look at this, in the first quadrant, it is horizontally simple, because if I were to draw a rectangle in horizontally, notice there is a clear left curve and there's a clear right curve. So being that this is horizontally simple, the first one I'm going to do is set up a dx dy. So that means I need to solve for my x equation. So going back to my circle here, that means that x minus 1, or x equals, let's go ahead and take it one step, 1 plus or minus the square root of 1 minus y squared. And then in the first quadrant, so y is going to go from 0 to wherever they intersect. So now I need to find the point where they intersect. Okay, so I set the two equations equal to each other, which would mean that 2x equals 1, x equals 1/2. Substitute that into either equation, I'm going to get y equals the square root of 3/4. So this point of intersection is at 1/2 and square root of 3/2. So that means my bounds for y are from 0 to 1/2. So setting up the formula, just to remind you, surface area is the double integral over the region R that I'm trying to find the surface area for. Square root of 1 plus f sub x squared plus f sub y squared. And then dA for whatever I decide for my area unit. Now, I'm going to do dx dy. So y is going to go from 0 to 1/2. X is going to go from, let's see, the right side of my unit circle equation. So that would be the square root of 1 minus y squared to the left side of my red circle equation. And that would be 1 minus the square root of 1 minus y squared. And then square root of 1 plus my partial with respect to x. So for my partial with respect to x, remember I'm using the function here that I'm trying to find the surface area of. So that's going to be x over the square root of x squared plus y squared squared plus y over the square root of x squared plus y squared squared. And this is dx dy. So visually, if you recall, this is the graph of a cone. So I have a cone that looks like this. I have this region that I'm integrating here and here. So basically what I'm doing is I'm finding the surface area of the cone, but only in that particular region if I were to look straight up. Now given that I have two circles, this would also be a possible candidate for polar, so now I'm going to set it up in polar. So polar is going to be r dr d theta. And actually what I want to do is I want to redraw the graph here because I want to talk about something that happens in polar. So in this equation, I've got my unit circle, which looks like this, and that would be the equation r equals 1. I have a circle that looks like this, and if I were to simplify that equation that I had up above, you are going to get r squared equals 2r cosine theta. So r equals 2 cosine theta, which would be that circle there. But if I do this in polar, I define it by what angles I'm integrating over. And if you notice, if I draw this line here, for this region here, r is being defined by the unit circle, x squared plus y squared equals 1. However, for this little region right here, this little curved part, x is being defined by the cosine equation. So I'm actually going to have to set up two integrals for this from 0 to wherever that point is of intersection, which actually we found out before, 1/2 square root of 3/2. And then from that point of intersection to pi over 2. So I'm going to do this one piece at a time. So let's start with the first part. Okay, so actually I think what I'm going to do is I'm going to set this up partially in polar, partially in rectangular, and then I'm going to convert it to polar once we get there. So starting with the first part, I'm going to have the integral for the angles, my integrals for my r, and then it's still going to be 1 plus fx squared plus fy squared, so I'm going to go ahead and put those in. 1 plus my partial with respect to x squared plus my partial with respect to y squared and then I know I'm going to be using r dr d theta, so I'm going to kind of mix it up here. Now let's see, the first red region, so that would be, okay, I'll do it in red so it kind of is consistent here. The red region would be the integral, so r radially starts at 0 and goes out to the unit circle, so r goes from 0 to 1, and then theta goes from 0 to that line where they intersect. So this point where they intersect, remember that tangent of theta equals y over x, so in this case tangent of theta equals square root of 3, and that's at pi over 3. And now what I want to do is actually simplify my integrand and then I'll convert it to polar. So if I simplify the integrand, I get 1 plus x squared over x squared plus y squared plus y squared over x squared plus y squared r dr d theta. And that actually works out nicely because notice in the second two pieces here, I get 1. So this integrates to 0 to power of 3, 0 to 1, square root of 2 r dr d theta. So that's the first piece. And now I need to add the little green piece that I have. So plus the integral for the little green piece, which would be from pi over 3 to pi over 2. And now this time, r is being defined by the origin up to my green circle curve. So that would be from 0 to 2 cosine theta. Integrand is still going to be the same, r dr d theta. So my suggestion when you try to write surface area in polar coordinates, actually write it in Cartesians first, and then once you have the integrand in x's and y's, then convert it to polar using your polar conversion formulas. Alright, I'm sorry this is after the quiz, but hopefully still in time for the test. Let me know if you have any questions. Thanks.